In this segment, we are going to discuss the process of collecting gases over water. This is an experimental technique that's done in the laboratory. I'll discuss the procedure in just a moment, but I want to mention here that collecting gases over water has applications to gas stoichiometry, also to Dalton's law of partial pressures. In Chem 22, this information is found in section 11.9 of your textbook. So in the laboratory, when we're collecting gases, we often implement an experimental technique called collecting the gas by displacement of water. So we fill a measuring tube or bottle with water, and then as the gas is produced, it's bubbled into the tube. Because it is less dense than water, it rises up and displaces or forces the water out of the tube. Right? So this process of collecting a gas by displacement of water is also known as collecting a gas over water. An important point to recognize whenever you are collecting a gas over water is to realize that the gas will always have a small amount of water vapor present mixed with it. Of course, water vapor referring to water in the gas phase. Right? So whenever you have liquid water present at a given temperature, there will always be a small amount of water in the gas phase above the liquid in equilibrium with it. This water vapor will exert a partial pressure in the mixture which has the gas that you are interested in collecting. So this partial pressure of water, called the water vapor pressure, must be taken into consideration when determining the pressure of the gas that you're interested in. Right? So how do we find out information about the water vapor pressure? There is something known as the water vapor pressure table, which lists the vapor pressure of water as a function of temperature. So in the Chem 22 lab manual, at the end of the lab manual where the appendices are, there's a solubility table of salts, and then on the bottom of that table, there is also a water vapor pressure table, which shows how the partial pressure of water varies above liquid water as a function of temperature. So you can access that information on this table. It's also present in your textbook in a table in section 11.9, I believe. So it's present in various places for you to gain access to. Let's do a gas stoichiometry problem involving collecting a gas over water. So we just completed an experiment involving collecting hydrogen gas through a single displacement reaction with zinc metal reacting with hydrochloric acid. So let's make a problem that involves that. How much zinc in grams must react with excess hydrochloric acid to produce 325 milliliters of hydrogen gas collected over water at 23 degrees Celsius and a barometric reading of 743 millimeters of mercury. Now, a couple of things to comment on before we unpack this problem and look at the solution. An important thing to mention is that as soon as you read the words collected over water, this is your signal. It tells you that the hydrogen gas that is being generated is wet, what we call wet. That means that water gas is mixed with it. And you have to take into consideration the vapor pressure of water when you do this calculation. So all of that is signaled with the words collected over water. When you see the barometric reading of 743 millimeters of mercury, a barometer, as you would recall, is a device that measures the pressure of the atmosphere. So this barometric reading is letting you know what atmospheric pressure is when the hydrogen gas was being produced and collected. So any stoichiometry problem, which this clearly is, it involves a chemical reaction, it's giving you a lot of data about hydrogen gas, and then asking you to calculate how much zinc metal had to react to produce that. All stoichiometry problems involve a chemical reaction, and you must have the balanced equation. We're now quite familiar with single replacement reactions and can easily put down here the single replacement reaction between zinc and hydrochloric acid to generate the hydrogen gas, as well as zinc chloride, which would remain dissolved in solution. Before we go through the calculations, we really need to appreciate the experimental setup for this reaction to understand what we need to do with this data. So I've shown here a drawing where you have a bottle where the reaction is going to occur. So you have your zinc metal in the bottle, and in this tube that is fitted into a 2-hole stopper, you have what we call a thistle tube. And a thistle tube has a little cup at the top, which enables you to add the hydrochloric acid solution into the bottle so that it can react with zinc and generate the hydrogen gas. Notice that this thistle tube must be submerged below the solution that's present so that when you generate the hydrogen gas from the reaction, it is forced to go into this second shorter tube that is connected with a rubber hose into a tube that I'm going to call a gas measuring tube that has volume markings on it. So as the hydrogen gas is produced, it goes up into this tube or into this bent glass fitted with a tube, and then feeds into what we call a gas measuring tube. Looks like an extra long test tube that has volume markings on it. Now at the start of this experiment, this gas measuring tube would be completely filled with water. No air pockets, just water present. And as the hydrogen gas is produced and moves through the tube into the gas measuring tube and goes up, it displaces or pushes the water out of the tube. So it's important to note here that you have a 2-hole stopper right here, and water, as it's being displaced out, can come out of the stopper as the hydrogen gas bubbles to the top and forces the water out. So we're collecting the hydrogen gas by displacement of water. The reaction will continue until we have generated, according to this problem, 325 milliliters of hydrogen gas. And we measure that hydrogen gas using the markings on the tube, right? Another thing to note is that when the reaction is complete, it is important to lower, so you raise or lower the gas measuring tube so that the water that is left inside of the tube is at the same level as the water in the basin outside of the tube. And of course, as I said, water can flow back and forth here. So you have water present in the dish pan and water present in the tube, and they are in continuous flow with each other. So at the end of the experiment, you lower the gas measuring tube so that the water levels inside and outside are equal. Why is that important? Right? That's important because you know that the pressure of the atmosphere is pressing down on the water level outside of the tube. Pressure of the hydrogen gas that you collected, and of course there's some water vapor also mixed with it, is pressing down on the water level inside the tube. And as long as those water levels are equal to each other, while water can siphon back and forth, then you know that the pressure of the atmosphere outside has to be equal to the pressure of the gas mixture of hydrogen and water vapor. And that's an important fact because you have a barometer that enables you to read the pressure of the atmosphere. So you can use that barometric reading to enable you to calculate the pressure of the hydrogen inside. While these water levels are being held equal, you make the volume reading of 325 milliliters. So let's look at this problem, right? We understand the experimental setup. Now, how do we do the calculation to be able to determine how much zinc metal had to react to produce this volume of wet hydrogen collected over water at 23 degrees Celsius and a barometric reading of 743 millimeters of mercury? You see that I've labeled the data here. We have our volume of hydrogen gas at 325 milliliters. So I'm going to convert that into liters because I'm lining myself up to do an ideal gas law calculation. If I have a V and a T, and I can use the barometric reading to get the pressure of hydrogen. So a volume of hydrogen, a temperature of hydrogen, and a calculation that gives me the pressure of hydrogen, I should be able to use the ideal gas law to calculate moles of hydrogen. So lots of data here to keep track of, and labeling it and organizing it is always a key to success. So here's the volume of hydrogen in milliliters. I'm converting it to liters. Temperature of hydrogen, 23 degrees Celsius. I'm converting that to Kelvin. And now right here, this calculation involves Dalton's law of partial pressures linked to this design, this experimental design. Barometric reading, pressure of the atmosphere, has to be equal to the pressure of hydrogen in the tube combined with the water vapor pressure, right? Because that is a gas mixture. This equality is true because these water levels are equal to each other. So here is that equation, a form of Dalton's law. And if I want to know what the pressure of hydrogen is, if I'm interested in that value, I can solve this equation for the pressure of hydrogen, which gives me pressure of the atmosphere minus the water vapor pressure. And again, we get that water vapor pressure reading from the water vapor pressure table. So I'm looking here, it's a function of temperature, water vapor pressure, and I read from the table that at 23 degrees Celsius, water has a vapor pressure of 21.1 millimeters of mercury. So, plugging in the data, the simple subtraction, I have the pressure of hydrogen alone in this tube, or the partial pressure of hydrogen is 721.9 millimeters of mercury with the uncertainty in the ones place. So I have a volume of hydrogen, I have a temperature of hydrogen, I have a pressure of hydrogen alone, and that sets me up to go into an ideal gas law calculation. So I'm going to use the ideal gas law to solve for moles of hydrogen, and that's going to take me right into stoichiometry. So here is the ideal gas law. I'm rearranging it to solve for moles of hydrogen, giving me PV over RT. And then I'm taking the data marked with the arrows and plugging it into the ideal gas law equation, solve for N. So I call this part of the problem the plug and chug part. Substituting in the data, chugging through the calculation on your calculator. Just looking at the dimensional analysis, I see Kelvin is canceling, millimeters of mercury, liters is canceling, and I am going to get a unit of moles, which is what I'm looking for, in the numerator where it should be. And when I do this calculation on the calculator, I got 0.0127 moles of hydrogen. And if you're interested, just pause the video and you double check and see if I got that right. So I have moles of hydrogen calculated from the ideal gas law, and I can come in and write here 0.0127 moles of hydrogen. At this point, we should see clearly the path to the finish line. I now know my moles of hydrogen, 0.0127 moles of hydrogen, and it's a very simple, straightforward stoichiometry calculation to solve for moles of zinc that had to react to produce this mole amount of hydrogen. So over here in the little bit of board space I have left, here is my 0.0127 moles of hydrogen. Using the mole to mole ratio from the balanced equation, which is 1 to 1, 1 mole of zinc reacts for every 1 mole of hydrogen gas produced, and then converting from moles of zinc into grams of zinc. When I did this calculation, I come up with an answer of 0.831 grams of zinc that reacted to produce this volume of hydrogen gas collected over water.